Hi everyone, my name is Wang, a Year 2 PhD student from Xi'an Jiaotong-Liverpool University. I'm glad to present our recent work, ResponsiveView, enhance 3D artifact viewing experience in VR museums. ResponsiveView design is an approach that is commonly adopted in web design. It allows 2D user interface to adjust automatically to device layout, enhance usability, navigation, and information retrieval by fewer user interactions. In this work, we draw inspiration from the concept of responsive design and apply it to virtual reality, aiming to enhance users' viewing experience in VR museums. In this section, we ground our work in how people view artifacts in physical museums and study how to map the viewing behavior in VR museums. Collections in physical museums are displayed in fixed locations with display cases or regulated viewing distance. In this context, museum professionals arrange the collections to align with human visual range, ensuring optimal visibility. Normally, they make decisions by the collection size. For some important and delicate collections, tools and systems such as magnifying glasses and interactive multimedia systems are sometimes provided to enhance the viewing experience. One significant challenge in VR museum is the stimulation of walking. It's hard for users to feel the sense of wandering around the museum and walking towards an object of interest. Realistic walking in VR demands tracking users' movement within a large physical space, which may not always be practical or feasible. In response, researchers have proposed alternative locomotion techniques. They all have their disadvantages. For example, in the studies of the point and teleport technique, researchers have measured variables such as the user's opposite value to the target point and the number of teleportation required to reach it. Visitors need to constantly adjust their position to reach a comfortable viewpoint in front of one specific artifact, where continuous locomotion will cause more serious motion sickness. Manipulations contribute significantly to the VR museum viewing experience. The use of magnifying glasses and interactive systems in physical museums serve two preliminary purposes. Firstly, to enlarge items or intrigue details, and secondly, they facilitate the rotation of 3D objects. It helps the visitors to view obscure sections, such as the bottom, backdrop, or interior. Those can map into two basic and important manipulations in VR museum. It is rotation and scaling. Museum professionals give guidelines to enhance visitors' viewing experience in real museum, but VR provides more viewing opportunities, and the real-world guideline may not work in VR environment. So we can conclude that so far, there is no specific guideline for fixed position artifact displays in VR museum, and it's unclear how hand-based interactions should be designed for artifacts viewing in VR museums. We designed Study 1 to identify the optimal viewing parameters, and based on the results of Study 1, we designed ResponsiveView, and in Study 2, we evaluated ResponsiveView in VR museum setting. Our Study 1 aims to answer the following two questions: investigate optimal pedestal height and viewing distance for fixed position artifacts viewing, and optimal size for handheld interaction with 3D artifacts in VR museums. To ensure environmental realism and system replicability, we use the Art Gallery Museum VR, produced by a professional art studio to construct the VR museum. 20 artifacts from Sketchfab were used. We keep the same lighting settings as the package deployed and use the same spotlight for each artifact. Participants were asked to complete 3 tasks towards one artifact: set the pedestal height, set the distance to artifacts, and resize the artifacts in hand. We collect 20 artifact size data, as well as the richness in details information. The user-defined pedestal height, distance to artifacts, and scaled artifacts data were recorded, as well as the user's eye level. 20 participants joined in this study. In total, 400 data were collected to run the regression, generated 3 predictive formulas. Based on the results of Study 1, we proposed ResponsiveView. We optimized the pedestal height by Formula 1 and used Formula 2 to determine the teleportation point in front of the artifact. When the user grabs the artifact in hand, the artifact will automatically adjust to a size calculated by Formula 3. We implement ResponsiveView with two relatively stable and popular imports, controller and head tracking, focusing on the actions, teleportation, and grab. Here is a demonstration video of ResponsiveView with controller-based import. Our study 2 is designed to answer question 3. Does ResponsiveView enhance the viewing experience of 3D artifacts in VR museums? A within-subject experiment with two conditions was designed, and the table 1 shows the difference between baseline and ResponsiveView. The baseline setting references the physical museum's display guideline. We built an exhibition room containing 10 artifacts. The participants were asked to teleport to view and describe the artifact from the fixed position display. Then they were asked to grab the artifacts to view and describe it from the handheld display. We collected system-logged data and used questionnaire to get some subjective data. We also collect participants' received visual information by their description, ask them to rate satisfaction with the fixed position and handheld display, invited them to discuss their preference and suggestions. With controller-based import, ResponsiveView demands fewer teleportation hover time with head tracking import, and a lower frequency of snap turns with controller-based import. When it comes to the usability and experience, participants perceive higher usability and better user experience with controller-based import, and at the same time, there is no significant difference found with hand tracking import. Statistically significant were found in the participants' perceived engagement with hand tracking import, and both controller-based and hand tracking import participants rated higher satisfaction for ResponsiveView than the baseline. Participants perceived higher performance using ResponsiveView with controller-based import and less frustration with hand tracking import. Detailed qualitative data and results can be found in our paper. Our study has some limitations. To facilitate quick understanding and implementations by non-graphic professionals, we use low-level factors of the artifacts that are easily accessible. We did not incorporate additional contextual information such as background details or the width and depth of the pedestal. Further work could refine the model by considering more factors and increase the sample size of training dataset. Users also report experience discomfort with the commercial handheld we used, highlighting the necessity for further economic consideration during the extended viewing sessions. Future research could also build on the current study to model user behaviors in VR. Other scenarios such as virtual shopping and assembling could also benefit from ResponsiveView designs that augment users' capabilities in movement and manipulation. To summary, our work improves 3D artifact viewing experience in VR museums. In the first study, we generated 3 predictive formulas, and based on the results, we proposed a ResponsiveView design, ResponsiveView, aiming to improve the locomotion and interactions in VR museum. And then an evaluation study revealed that its positive effects on both controller-based and head-tracking imports. Furthermore, we formulated design recommendations for 3D artifacts viewing, and we believe further work can build on those guidelines and validating and refining the designs through user behavior modeling. And thank you for your listening. More details can check in our paper, and if you have any questions, please feel free to contact us.